Welcome class to the video for handout unit 7B, combining probabilities. So this is a great math 1030 topic. We're going to start out with and probabilities. Okay, so that's the key here is and probabilities. These are joint probabilities, and probabilities are probabilities that two events can occur. What's the probability that two events will occur? So and probabilities are the probability that two events will occur. Now, there are and probabilities and there are either or probabilities. Okay, those are the two types of probabilities we have in this section. Among the and probabilities, the events can be independent or they could be dependent. Okay? Independent means that they do not influence one another. Dependent means that they do. So what are independent events again? Those are events that are independent if the occurrence of one event does not affect the probability of the other occurring. So events are independent if the occurrence of one does not affect the probability of the other occurring. Okay. Let's do a couple of examples here. Example number 1, tossing two fair coins. What is the probability of getting two heads? Okay, at the end of last section, we calculated this by putting out all of the possible ways to get to outcomes of two fair coins. Here we can take a look at the events independently, okay? And so we will go ahead and do the probability of getting heads when you toss two fair coins. So I'll abbreviate it like that. That's the same thing as the probability of heads on coin 1 times the probability of heads on coin 2. Okay, so since these are called and probabilities, there's two different ones, and these are independent, so we're just going to simply multiply them. Okay, and watch and you'll get the same answer as before. So remember that this was 1/4. Okay, so the probability of getting heads on coin 1 when you toss it is 1/2. The probability that you get heads on coin 2 is also 1/2. When you multiply them together, you get 1/4. Okay, so that is the same as before. So and probabilities can be found by multiplying. Let's go ahead and do example number 2. We're going to toss two fair 6-sided dice. What's the probability of getting a double 4? Which means that a 4 will come up on one die, and the 4 will come up on the other die. Okay, so the probability of getting double 4 is equal to the probability of getting 4 on die 1 multiplied by the probability of getting 4 on die 2. Okay, so that is equal to 1/6. Okay, because there's 6 numbers and 4 is one of those numbers. Multiply by 1/6, because the same probability will happen on the other die. Remember, they're not affected, they're independent. And that equals 1/36. Okay, so when you toss two die, one die is not going to affect the other one. Okay, so in summary, the formula for calculating probabilities of independent events, their AND probabilities, is the probability that A and B occur is equal to the probability of A occurring times the probability of B occurring. Let's say that you have multiple independent events, like more than two. Or we can say that the probability of A and B occurring and C occurring, and as many as you want, is equal to the probability of A times the probability of B times the probability of C times however many you want. Okay. So there's our formula. Let's go to dependent events. The next type of AND probabilities is called dependent events. Okay. Events are dependent if the occurrence of one event does affect the probability of the other occurring. So we have events are dependent if the occurrence of one event does affect the probability of the other occurring. Okay. For example, we're going to think about a standard deck of cards. Okay, just like we talked about last class, there are 13 cards of each suit or each group. And 52 cards total. So we're going to take out a card. What's the probability of drawing a queen, keeping it out, and then drawing another queen? Okay. When we don't put the card back in, we call it without replacement. Okay. So we want to draw two queens one at a time without replacement. So that's the probability that we're thinking about. So the probability of drawing two queens one at a time without replacement. Okay. So in order to find this probability, we need to take that's equal to the probability of getting the first queen times the probability of the second queen when given that one is out. Okay, so that will affect our probability, our theoretical probability here. So the chance of getting the first queen, there are 4 queens in the deck, there are 52 total cards. We multiply that by the probability of getting the second queen given one is out. So if one card is out, we have 3 queens left, and there's 51 cards left. Okay, so we want to multiply those two fractions together. And we get 12 over 2,652, which is equal to 1 over 221, which is about equal to 0.0045. Okay, so that's this very small probability of pulling 2 queens, given one is out. Let's think about a box of chocolates, our next example. There are 5 chocolates and 5 caramels in a box. What is the probability of selecting one chocolate and then another chocolate? Okay, so we're thinking about the probability of getting 2 chocolates, one at a time, without replacement. Okay, that's equal to the probability of getting the first chocolate times the probability of getting the second chocolate given one is out. So the probability of getting 1 chocolate is 5 out of 10 because there's 5 chocolates and there's 10 total pieces of candy. And multiply that by the probability of getting the second chocolate given 1 is out, which is there's only 4 chocolates left and there's only 9 pieces of candy left. And so that's equal to 20 over 90, which is equal to 2/9, which is equal to, or about equal to, 0.22. Okay. So thus, the formula for the probabilities of dependent events occurring of AND probabilities is the probability of A and B occurring when they are dependent on each other, probability of A times the probability of B given A is how you say it. Okay. And so if you want to do multiple events, more than 2, the probability of A and B and C and however many you want is equal to the probability of A times the probability of B given A times the probability of C given A and B, and so on. Okay. Now this brings us to our next category, large category of probabilities. These are called either-or probabilities. So if one happens or the other, then we need to take that into account. What does that affect our probability? So a kind of a definition is either-or probabilities are the probability that one or another event will occur. And these are typically larger probabilities because they don't both have to occur at the same time. They could be one or the other. So that could increase your chances of the event coming true. Now, in either-or probabilities, we have, this or is key there, we have non-overlapping events and overlapping events. Okay, so non-overlapping and overlapping. Okay, so what are non-overlapping events? They are events that cannot occur together. Okay. For example, if you take a 6-sided die and what is the probability of rolling a 1 or a 6? Okay, so you have 1 or 6. They can't occur together. Your dice is going to reveal or have one or the other as a result. So we think about the probability of rolling 1 or 6 is equal to the probability of rolling 1 plus the probability of rolling 6. Now, since they don't have to occur together, then we add the probabilities. So we'll add 1 6 plus 1 6, and we get 2 6, which is equal to 1/3, which is about equal to 0.33. Okay. The probability of rolling a 1 or a 6 is about 1/3. Okay, let's take a look at a standard deck of cards. What is the probability of drawing an even card or an ace? Okay, so think about probability drawing even or an ace. Okay, now the even means 2, 4, 6, 8, or 10. So you have the probability of drawing 2, 4, 6, 8, 10 plus the probability of drawing an ace. Okay, so what is the probability of drawing a 2, 4, 6, 8, or 10? Now, there are 4 suits, and I have 5 numbers here. So that's a probability of drawing 20 cards out of the 52. And now that the probability of drawing an ace. Now, ace is 1 card, but each suit has the ace. So we have 4 aces in the deck. So that's 4 out of 52. Okay, so we're going to add those together. We get 24 out of 52. Which is equal to 4/13, which is equal to, or about equal to 0.31. Okay, so you have a 0.31 chance, or almost 1/3, of drawing an even nut card or an ace. So let's think about a formula for generalizing this idea. Calculating the probabilities of non-overlapping events. So we have the probability of A or B happening. That's equal to the probability of A happening plus the probability of B happening. Okay. Or we can think of probability of multiple things, A or B or C or whatever, however many more you want. That's equal to the probability of A plus the probability of B plus the probability of C, plus however many more there are. Now we're going to look at overlapping events. These are either or probabilities that are overlapping events. So what are overlapping events? Well, they are events that can occur together. So in our first example, we have a room where Democrats and women and men and Republican women and men are debating. So we're going to take a look at the focus on the group of Democrats and women. There's 20 people in the room. Okay, 10 are Democrats, 10 are Republican, 10 are men, 10 are women. 5 of them are Democrat women and 5 are Republican women. What is the probability of selecting a woman or a Democrat? Okay, so this is the or. We need to think about a woman or a Democrat. So let's go ahead and write down a probability. We're translating our situation into English. Okay, so we think about the probability of selecting a woman. If you choose anybody at random, okay, now that's equal to the probability of selecting a woman plus the probability of selecting a Democrat move this over just a tad. Move it over a little bit more. Okay. But we also need to subtract off the overlap, okay, since this is overlap. There are 5 Democrat women in there. So if I'm selecting all of the Democrat people and all of the women people, then there's some that will overlap. 5 to be exact. Now, let's take a look at, we want to subtract off the probability of selecting a woman and a Democrat. The one that fits both categories, because they will be double counted. Now, the probability of selecting a woman is 10 out of 20. Okay, so there's 10 men and 10 women. The probability of selecting a Democrat is also 10 out of 20. 20 are Democrat, 20 are Republican. But 5 of them are women and Democrats, so we take away 5 of those to not double count them. And what we get is we get 15 over 20, which is equal to 3/4, which is equal to 0.75. Okay, so the probability of selecting a woman or a Democrat is 0.75. Okay, so high chance of doing one or the other. Let's take a look at another example. What is the probability of drawing a queen or a spade? Or is key there. Queen or a spade. So the probability of drawing a queen or a spade from a standard deck of cards, all shuffled, all put in front of you. Okay, the probability of doing that is equal to the probability of drawing a queen plus the probability of drawing a spade minus the probability of drawing a queen and a spade. Okay. Now this card right here is the Queen of Spades. Okay. So it's one card that can combine both of them together. So we have the probability of drawing a queen, there's 4 queens out of 52 cards. We're going to add that to spades. There are 13 spades out of 52 cards. Then we're going to subtract off the queen of spades because that's the one card that's double counted. So we'll subtract off that one double counted case. And what we get is we get 16 out of 52. 4 and 13 is 17, minus 1 is 16, which is equal to 4/13, which we know is about equal to 0.31. Okay. Now let's think about a formula. Generalizing these situations, we'll think about a formula. So the probability of overlapping events, the probability of A or B when they overlap, okay, is equal to the probability of A plus the probability of B minus the probability of A and B. Okay, so you use this formula when they are overlapping. There's one thing that's in common between the two groups. Okay. Our last topic for this video is the at least once rule. Okay, we want to find the probability of getting at least one occurrence of something. So here's all the outcomes of a toss of 4 coins. You can have all heads, you can go down to all tails, every combination in between. What's the probability of getting at least one head? Okay, so the at least one head means that I'm going to have one head or more in all of my outcomes. Okay, notice that this row right here has at least one head, and this one and this one. There's at least one head in all of these outcomes except for the bottom one. Okay, notice there's at least one head in all of these. Okay, but we only found that out by mapping everything out. So for more complicated models or experiments, we wouldn't want to map everything out. We want to be able to just find a way to calculate the at least once rule. Okay, so what we're going to have is, in example 1, we have toss of 4 coins again. What is the probability of getting at least one head? Now, the probability of getting at least one head plus the probability of no heads equals 1. Okay, notice that I have all of my possible things listed out. There's the probability of at least one head in all the blue arrows. The green arrow indicates the probability of no heads, which is only one case out of the 16, one event. And so when you add up all 15/16 of them plus the 1/16, you get 1. So the probability of at least one head plus the probability of no heads is equal to 1. Again, we'll use algebra to our advantage, and we're going to solve it for a probability of at least one head by subtracting off the probability of no heads from both sides. So probability of at least one head is equal to 1, subtract the probability of no heads. Okay. Now, how can I calculate the probability of no heads? Well, the toss of 4 fair coins is the same if you toss them all at once or one at a time. Okay. So we know that this is equal to 1 minus the probability of no heads in toss 1. times the probability of no heads in toss 2. Okay. Times the probability of no heads. Oops. In toss 3. Times the probability of no heads in toss 4. Okay. So we're multiplying all of those together. We use brackets to help us there. We know that that's equal to, actually let me make that a little bit easier to read. Okay, so that, I'll just write it this way. So the probability, again, so let's review. The probability of getting no heads is the same thing as the probability of getting no heads on all the tosses. Okay, so that's equal to 1 minus the probability of no heads for toss 1 times the probability of no heads toss 2 times the probability of no heads in toss 3 times the probability of no heads Okay, got it. I'm going to simplify the really long part here and say that's 1 minus the probability of no heads to the 4th power, okay? Because notice that I'm multiplying each one of these, the same thing, multiple times, okay? So that means that we can use exponents to help us. That's more accurate there. Now, the probability of not getting heads is like getting tails, which is actually 1/2. So it's 1 minus the probability of getting tails, the 4th power, equals 1 minus 1/2 to the 4th power, which is equal to 1 minus 1/16, which is equal to 15/16. Okay. All right, so that confirms what we kind of explored manually. So this calculation is very helpful. Let's try to take a look at this one with the toss of 2 fair 6-sided dice. When we throw 2 fair 6-sided dice, what's the probability of getting a sum of at least 7? Okay. So the probability of at least 7, okay, you could get 7, an 8, or a 9, or a 10. Okay, we're going to add that to the probabilities of all the other ones. Probability of getting 1, plus the probability of getting 2, plus the probability of getting 3, plus the probability of getting 4, plus the probability of getting 5, plus the probability of getting 6 is equal to 1. Okay. So that we know that there are 12 of these things. 12, you can get 12. So the probability of getting at least 7, which means 7, 8, 9, or 10, or 11, or 12. So we use our algebra. 1 subtract the probability of getting 1, plus the probability of getting 2, plus the probability of getting 3, plus the probability of getting 4, plus the probability of getting 5, plus the probability of getting 6, which is equal to 1 minus. Now the probability of getting 1 is 0, because you can't get 0, you can't get 1 with 2 dice. Probability of getting 2, okay, which is 1 out of 36. There's only one way to get 2. There's 2 ways to get 3, 2 and 1 and 1 and 2. And so on, 3 ways to get 4, and 4 ways to get 5. And 5 ways to get 6. Okay. So that's equal to 1 minus 15 over 36, which is equal to 21 over 36. Okay, so there's 21 ways to get 7, 8, 9, 10, 11, or 12. And we simplify that to 7/12. We have our answer. So the formula for calculating the least once rule is the probability, and the key is at least once. Okay, so look for in the homework, look for at least once if you want to use this one. The probability of at least one event A in n trials. Okay, so we have a bunch of things that we can do, like coin tosses for n trials, is equal to 1 minus the probability of no A in n trials. Which is equal to 1 minus the probability of not A to the n power. Okay. All right, so there's our video. Please let me know if you have any questions.